Our today's lecture is on the constraint least square restoration. Now, so far we have seen two image restoration approaches. The first was the classical inverse filtering approach, and then in the last class we also saw the Wiener filtering approach. Now, in the case of Wiener filtering approach, what we saw was that it is optimal in the sense that if we consider the average effect, okay, in that sense only it is optimal, because the computation of the Wiener filter is dependent upon the computation of the correlation matrices for the image as well as the noise. Alright. So it is only optimal in an average sense. But what we would like to have is to design filters which are optimal with respect to just that particular image only. I mean, with respect to the given image also it should be optimal, and that's why an entirely new technique has to be proposed. Now, one thing which should be told is that in the last class we had this kind of the objective function, right? Where we had said that for the constraint restoration problem, we have to minimize this expression, alright? Jf being the objective function, qf square plus alpha into g minus hf square minus n square, basically. This is coming as the constraint term, and we were choosing an operator q, a linear operator q on this estimated image f hat. Alright. Now, there we had said that the solution is indeed dependent upon the choice of q. So, it depends that what type of a minimization function we are actually going to choose. Alright. And I mean, there could be various figure of merit for optimality, and one such optimality measure could be a measure of smoothness, where we will define a smoothness factor, okay, and we will minimize the smoothness parameter, okay, over that image. All right. So that means to say, if somebody gives us the, I mean, if we consider the image f of xy, alright, we are going to consider the minimization of its, I mean, some measure of smoothness, and as a measure of smoothness we can take the second derivative operator, okay, so that if we can minimize the second derivative function of this image, okay, and square it up, okay, that particular expression we are going to minimize. So we are going to consider the minimization of del 2f xy del x square plus del 2f xy del y square. This square we are going to consider its minimization. Okay, so this is the second derivative, and square of that we are going to minimize. Now, obviously, second derivative operator picks up all the discontinuities in the image function. Alright, and what we are going to minimize is the square of those discontinuities, so that the estimated image is smooth. Okay, that is the criteria which we are applying. Now, we have already seen that how to implement a second derivative, I mean, how to implement a second derivative operator while we were discussing about the high-pass filtering, and especially we discussed on the Laplacian operator, etc. Okay, there we had seen that computation of this second derivative in x direction and second derivative in y direction, this can be done if we convolve the image f of xy with another function p of xy, okay, which is given as follows. So we can obtain a second derivative by convolving with an operator pxy of the form 0, -1, 0, -1, +4, -1, 0, -1, 0. Okay, this is going to be a 3 by 3 operator, and we are going to convolve the image with this, and then only we will get the second derivative filtered image. Okay, and we have to minimize basically the square of that. All right. Now, if we are going to perform the second derivative, if we are going to perform the convolution, okay, then one approach which we can adopt is to extend both the functions fxy as well as p of xy, okay, to a larger size matrix, and then we can do the convolution in the true sense. So what we are going to do is that we are going to extend this function p of xy, okay, as we discussed in some other class. Okay, now consider the extended function of p of xy. Now call it pexy, signifying the extended function, and pexy is going to be equal to p of xy, that is to say this defined function for what? For what limits? When 0 is less than or equal to x is less than or equal to 2, and when we have y also lying between 0 and 2. All right. So this is what we are getting, and in all other places, what are we going to have? Because let us consider that the size of the image fxy is going to be m by n. All right. So we are going to have pexy equal to 0 for x lying between 3 and m minus 1, or when y lies between 3 and n minus 1. Okay. So what we are going to do that, this f of xy we are not choosing of size mn, rather let us say we choose f of xy as such, of size a into b. Okay, that means to say a rows and b columns, a by b being the size of fxy, so that what our m and n should be is what should be the limit on m?
A plus 2.
M should be, yes, a plus 3 minus 1 basically. Okay, because it is a minus 1 plus this, and since this is 3 by 3, so basically we are getting m greater than or equal to a plus 2, and n is also going to be likewise greater than or equal to b plus 2, so that we are extending both the image as well as the convolution operator, that is to say p of xy, okay, to an image of size m by n. All right. And by considering the extended functions, okay, let us consider the extended functions as follows. Our net convolved result, okay, gexy can be written as the convolution expression, that is to say using a double summation we can write this as x is equal to 0 to m minus 1 limit y is equal to 0 to n minus 1 if e of xy, okay, pe of x minus I think we have to use another variable, so let us do it this way. Ge of xy, actually speaking, Ge of xy should be written as a double summation. M is equal to 0 to n minus 1, then n is equal to 0 to n minus 1, then f e mn and pe x minus m y minus n, because this xy are the same as the ge xy. Okay, so it is pe x minus m y minus m, y minus n, and this is to be integrated, rather in the case of discrete domain, a double summation should be applied with limits m is equal to 0 to n minus 1, n is equal to 0 to n minus 1. So that means to say, we are assuming that capital M and capital N are going to be the same. So that means to say, we assume this to be a square image. Alright. So, this is the, net convolution expression that we are getting. Alright. Now, from this convolution expression, after all, what we are going to consider is that we are going to write again this equation in the form of a matrix representation, in the form of an equivalent matrix representation, and you are seeing that convolution expression when you write in the matrix form, okay, because last time also we considered, we had to consider a very similar situation where we were obtaining the degraded image as convolution of the original image and the point spread function, or rather the impulse response function. Okay, and then when we had considered the representation in the matrix form, then the impulse response function, okay, which was actually the convolving function, had become the a block circulant matrix. Okay. Now, very similarly, our now objective is to represent this PE x minus m y minus n, this function, okay, in the form of a block circulant matrix, so that again we can diagonalize the matrix, okay, in a way which we already know. So, let us consider a block circulant matrix of, a circulant matrix of this form, okay. Let us say that we define, we consider a particular row of this extended PE. So we are considering the function PEXY, okay, and consider a particular row J. Consider a particular row J, and let us construct its circulant matrix. Okay, so the circulant matrix for row J, circulant matrix for row J of PEXY can be written as, let us call that circulant matrix by the symbol C, and we are indicating some suffix J, okay, so that it is the circulant matrix of the jth row. Now, what is going to be the matrix size? We are considering now capital N number of elements. The image has become an n by n image, okay, so that row J of PEXY is going to have how many elements? N number of elements, okay. So we are going to consider an n by n circulant matrix. Alright, so that can be written as follows. Yes, tell me what should be the first element? PE J0, yes, because J will remain everywhere, J will remain, since it is a circulant matrix composed of the jth row, that is why J will remain always, okay, and the rest of the elements can be written as PE J n minus 1, etc., 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 up to PE J1, alright, and the next element will be PE J1, PE J0, okay, PE J2, alright, and the last row will be PE J n minus 1, PE J n minus 2, PE J0. So we are going to construct a circulant matrix of this form. This becomes a circulant matrix, isn't it? Alright. Now, using this circulant matrix for jth row, this is the definition of circulant matrix for the jth row, and using the circulant matrices for the other rows, okay, let us now compose a block circulant matrix, okay, a block circulant matrix consisting of all these CJs, alright, and let us write it in this form. So we define a block circulant matrix, call it a matrix C, okay, which is defined as C0, C, call it m minus 1, C m minus 2, okay, etc., etc., then C1. All right. I mean, actually speaking, later on we are going to assume a square matrix size, but there is nothing wrong if, for the time being, you keep this as m, okay, because we are ultimately going to consider the case of m equal to n, okay. So C1, this is going to be C0, this one Cm minus 1. I mean, like the usual way we construct block circulant matrix, and the last row is going to be Cm minus 1, Cm minus 2, Cm minus 3, etc., etc., up to C0. All right. This is our circulant. This is our block circulant matrix. All right. So now, what are we going to do? Well, we had a convolution expression of this form. Correct. Let us take, okay. Let us take the image, extended image size to be m by n only, then it goes from m is equal to 0 to capital M minus 1. Anyway, since this is the expression for the convolution, all right, we can now represent this in a matrix form, all right. So what we are again going to do, we are going to row order, do a row ordering on the image so that GE now becomes an mn by 1 dimensional vector, okay. The given image FE mn, okay, rather FE is going to be, in our case, FE is going to be the estimated image basically, or rather the original image you can say, okay, estimated image, and PE is going to be the convolving function, okay. So in terms of matrices, and mind you, what we have to minimize is not this expression alone. What do we have to minimize? This expression square, because we are going to consider minimization of the square of this second derivative, okay. So if you are writing the square term, okay, then it is very easy to see by very simple matrix deductions, okay. It is possible to see that what we are getting is something like this, that our minimization expression, that our ultimate objective will be to minimize the square of the second derivative term, or rather which can be written as ft ct, okay, cf. All right. So this is the minimization of what we have to do ultimately, okay. Now, since C happens to be a block circulant matrix, this you can easily verify that it reduces to a matrix of the form CF square, okay. It reduces to minimization of this particular expression. All right. Now, since C is a block circulant matrix, okay, we can diagonalize that block circulant matrix, okay. So block circulant matrix can be diagonalized by this expression. Let us call the diagonal matrix to be E, a matrix E, okay, which can be written as, in terms of C, what you can write? In the case of diagonal matrix,
W into W inverse.
W inverse C W, okay. We can write C as W E W inverse, or we can write E as W inverse C W. All right. Where E happens to be a diagonal matrix. E is a diagonal matrix. And tell me, what are going to be the elements of this diagonal matrix?
B, F, T, F, C.
So the elements of diagonal matrix are going to be elements of E will be nothing but the 2D discrete Fourier transform of what? Of PE, xy, okay, and call the 2D DFT of PEXY to be P of capital P index KL, okay, capital P index KL. Let us consider that is the KLth element of the 2D DFT of PEXY, okay, and the diagonal matrix elements, okay, will be like this. All right. Now what we are going to consider is the minimization of this particular expression. Fine. Now we have to make, now if we have to apply our constraint restoration problem, okay, that means to say minimization of this expression which we had considered yesterday. Now if we have to consider the minimization of this, we have to make a suitable choice of the matrix Q. All right. And now what should be a good choice of the matrix Q? Let us choose matrix Q as the matrix C. Okay. So let the matrix Q is the matrix C. Okay. Then one thing which we can do is that we can see that since we have to do minimization of QF square, okay, norm of QF square, what is the way by which we can write? This can be written in the matrix form. This square can be written in matrix form as QF transpose, okay, QF, correct? And what is this going to be? This is going to be F transpose Q transpose QF. All right. And since we have chosen Q is equal to C, okay, our minimization, okay, which we had got, okay, should be a minimization of FT, CT, CF. This is exactly what we wanted, isn't it? So now we can very well choose Q is equal to C because that satisfies our minimization criteria. Okay. So that means to say ultimately we have to minimize this QF square. All right. Now what is the nature of the optimal solution for the constraint restoration? Try to recollect. What is going to be the optimal solution? So whatever optimal solution we had got yesterday, okay, there we will be substituting Q is equal to C. All right. So the optimal solution is given by please look at it. F hat equals to what? Can anybody have a quick look at the last class notes? H transpose H plus gamma C transpose C. Okay, C transpose C. This entire thing inverse H G. Okay, this is going to be the optimal solution. Okay, and now again we can write the H matrix and C matrix in their respective diagonalized form. Okay, we can write H matrix and C matrix in diagonalized form and they become W D star D W inverse plus gamma W E star E W inverse, this entire thing inverse multiplied by W D star W inverse, okay, G. Okay, this is what we will get if we simply substitute the relations. H is equal to what? H is equal to W D W inverse and C is equal to W E W inverse. Okay, so we will be directly getting this. And now let us transform them to the frequency domain. So that means to say multiplying the left hand side as well as the right hand side by W inverse. Okay, so what we get after multiplying by W inverse and doing manipulations, okay, we are getting W inverse F hat, okay, equals D star D, okay, plus gamma E star E, okay, inverse D star W inverse G, okay. And from this, I think it is quite easy to derive the derive what? Derive F hat KL. That means to say KLth component of the frequency domain. So F hat KL, and tell me what it is going to be. What is going to be the denominator term? Excellent. Mod of HKL square plus gamma. This is going to be mod of PKL. Call it PKL, okay, because that is going to be the 2D DFT of the extended function PE, okay, the extended convolving function PE, okay, and in the numerator we are going to have H star KL, okay, and this entire thing must be multiplied by G of KL. Okay. Now, one thing which we have to see is that how do we determine this gamma? Okay, because as I was telling during the discussion of this equation, that gamma, or rather in this expression we are having alpha, but we know that it is equal to alpha is equal to nothing but 1 upon gamma, and there we had said that gamma must be chosen so that ultimately what is it that we are going to satisfy, or ultimately what relation are we going to satisfy? Our norm of n square should be equal to G minus HF, norm of G minus HF square. Alright, so what we have to do is we have to adjust gamma so that, I mean, this was our equation. F hat was equal to H transpose H plus gamma Q transpose Q inverse H transpose G, okay, and gamma should be adjusted so as to satisfy the constraint that our ultimate G minus HF, okay, square should be equal to n square, norm of n square. And mind you, this was our original condition, right? And we must adjust gamma in this particular manner. But the difficulty is that we don't have F with us, okay, we have only G with us, alright, and we are going to estimate F hat, alright. So we cannot compute G minus HF, what we can compute is G minus HF hat, alright. But if we can fulfill the constraint that G minus HF hat square becomes equal to norm of n square, then we can say that F is correctly estimated as F hat, alright. So now what we have to do, if it is possible for us to measure this n square, okay, if from the given image we can measure this noise power n square, okay, in that case it should be possible for us to make an adjustment on this F hat, okay, so that we fulfill this. So that means to say our gamma must be adjusted. Now gamma adjustment will give what? If we adjust gamma, we are going to find a new value of f hat, and that new value of f hat we will be putting here and seeing that whether we are fulfilling this criteria or not. If we are fulfilling the criteria, if it is equal to n square, or if it is very very close to n square within some reasonable accuracy limits, if g minus hf hat square is very close to n square, I mean either exactly equal to n square or very close to the expression for n square, okay, then we stop our iteration there. Otherwise we must evolve an iterative technique, okay, whereby we will be adjusting this gamma, okay, this parameter gamma, so that we get new estimate of f hat and try to fulfill this criteria, okay. And till the time we reach g minus hf hat square equal to n square within some reasonable accuracy, okay, we must proceed with this iteration. So what we are going to describe now is an iterative method whereby this gamma will be adjusted with each iteration depending upon our value of g minus hf hat, okay. And that g minus hf hat, what is that going to be? That is going to be another vector. We will call that as a residual vector r, okay. Anyway, we are coming to this expression, okay. So we are defining a residual vector r, okay, which is given by g minus h f hat, okay. Now if we have r equal to g minus h f hat, then substituting this value of f hat, okay, this was what we had got as f hat, alright. Only thing is, in this particular case, instead of putting it as q, we will be putting c, alright. So just substitute this f hat, okay, in this expression to get the residual vector. So the residual vectors expression is going to be r vector equals g vector minus h transpose h plus gamma c transpose c, this entire thing inverse h transpose g. Alright, this is going to be our residual vector. We are going to call it as a residual vector. Now this residual vector is a function of what? It is very much a function of gamma. Alright, so let us define a function of gamma, okay. We call that function as phi. So a function phi of gamma, let us say, is defined as r transpose r. And what is that going to be? That is going to be the norm of r square. This is nothing but r square. Agreed? Okay. And it can be seen that this phi gamma function which we are defining like this, okay, it can be shown that this phi gamma is a monotonically increasing function of gamma. So by having a knowledge of this, it comes to our advantage. So that means to say, after computing the residual vector r, okay, we definitely know that in which direction gamma must be adjusted, because we know it for certain that phi of gamma is going to be a monotonically increasing function of gamma, okay. So we have to adjust gamma, okay, gamma should be adjusted so that norm r square is equal to norm n square. Ideally r square must be equal to n square, isn't it? Okay, r is a residual vector, so r square must be equal to n square. But can it be exactly so? It cannot be. So what should be the mathematical expression? We must define some accuracy factor A. Okay, so gamma should be adjusted so that R square should be n square plus minus A. Okay, where A is an accuracy factor. Excellent. So what is unknown so far? N. So we have to make a good estimate of n square. Okay, only then we must be able to, and we have to choose some accuracy factor, of course. Okay, only then we will be able to compute this R, okay, properly. I mean, we will be able to see that whether gamma is appropriately adjusted or not. Okay, so n square must be known to us, and this is very easily computed from the noise variance. So all that we have to know is the noise variance, and if we take the noise as eta xy, okay, in our case we will take eta exy because we are working on the extended function. So we take eta exy, and the variance, the noise variance for eta exy can be written as sigma square eta equal to expectation of eta exy minus what? Minus the mean noise, eta e bar, let us write it. Okay, this thing square and overall expectation of this, which can be written as expectation of eta square e xy, okay, minus eta e square. Okay, and what is going to be our eta e bar? It is very simple. For the case of m by n image, what are we going to have? 1 upon m minus 1 n minus 1. Okay, this is going to be the normalizing factor, and overall it should be, we must double sum up eta e xy over x and y. Alright, so thereby we will be getting eta e bar. Okay, and since expectation of eta square e xy can be computed as nothing but the summation of all the eta squares, I mean mean of all eta squares, if we now take, that can be substituted for the expectation, and thereby we will be writing sigma square eta equals 1 upon m minus 1 n minus 1, okay, summation x summation y eta square e xy minus eta bar e square. Okay, and this expression can be written as what? Norm of n square, alright, divided by m minus 1 n minus 1 minus mean noise eta e square. Okay, or rather from this expression we can get n square as m minus 1 n minus 1 sigma square eta minus eta e square. So if the noise variance eta square sigma square eta and the mean noise eta square eta e square is known to us, okay, if these two things are known to us, we get an idea of n square. Alright, yes, any question? Previous one, yes. Alright, so this was our expression, and from which we are getting
sigma square plus eta e square. Sigma square plus eta e square.
Sigma square plus eta e square. Oh yes, you are correct, yes, this is what it is. Fine, so this is the expression for n square. Okay, and now our iterative approach okay, can be summarized like this. Okay, so we are now working on an iterative algorithm. So what is going to be the step 1 of our iteration? We have to obviously choose an initial estimate of gamma. Okay, so choose initial gamma, and also in the first step we must have an estimate of, obtain an estimate of n square, and I think rest of the things can follow very simply. Since you know what gamma is, what you will simply do? You will simply compute f hat, okay, and then using this gamma you will be able to compute this expression. So that means to say you will be able to compute f hat of kl. Okay, so in step 2 we compute f hat kl and obtain small f hat, that means to say the estimated image, by taking inverse DFT. Alright. Now in step 3 what we are going to do, we are going to compute the residual vector R. Alright, and subsequently we are going to compute phi gamma as norm of R square. Agreed? Okay. Now after R is computed, okay, or rather after phi gamma is computed, okay, rest of the things are pretty simple for us. Step 4, if phi gamma is less than norm n square minus a, what are you going to do? You are going to, I have already told that phi gamma is monotonically increasing function in gamma. Okay, so we must increment gamma. Okay, that's to say in case A, and in case B, if phi of gamma is greater than norm n square plus a, then obviously you must decrement gamma. Okay, and after doing this, after incrementing or decrementing, okay, what are you going to do? In which step will you come back? Again we will come back to step 2, means with the new gamma, new value of gamma, we will have a new estimate of f hat kl and obtain a new f hat, okay, new f hat vector, and then we will be computing R, that is to say the residual vector in the second iteration, and then proceed this thing in a loop. Okay, and when does the loop stop? When phi gamma lies within the limits n square plus or minus a. Alright, so step 5 we can say return to step 2 and continue unless phi of gamma is equal to n square plus or minus a. Now obviously, I mean strictly speaking I should have written phi gamma lying between n square minus a and n square plus a. Alright. Now if phi gamma lies between n square minus a and n square plus a, okay, then what are we going to do? We are going to stop our algorithm there, and that particular value of gamma will be retained. Alright, that particular value of gamma will be retained, and corresponding to that gamma, whatever f hat of KL you get and whatever small f hat vector you get by taking the inverse DFT, that small f hat vector is going to be what? The restored image. Alright? So this is what is described as the constrained least square restoration. So let us summarize it once again. What we have essentially done is, or rather in this kind of an algorithm, we see two characteristics. Firstly, that it is going to be an iterative algorithm, okay, and the second characteristic of this algorithm is that it does not require the knowledge of image correlation, or rather you don't have to do the optimization in average sense, rather taking an ensemble of image. That is not exactly, that is not really required. You can optimize with respect to the given image only, okay, and what you ought to know about the given image is the estimate of its noise, n square, and n square, as I have shown, okay, can be known if you know how to compute the if the noise variance is known to you and if the mean noise is known to you, then it is possible to estimate n square, and once n square is known, then according to this algorithm we can iteratively improve upon our estimate of gamma, and in turn we get better and better estimate of f hat. Alright, so this is the essence of this approach. And constrained least square restoration, both Wiener filtering approach as well as constrained least square restoration approaches, okay, they have been tried out widely in case of image restoration problems. Alright, now we are not going into any further details of image restoration, okay. From the next class we are going to start a new topic, that is on the image segmentation. Thank you.